In this question, we are given that the count of bacteria is 600 after 20 minutes and 1600 after 35 minutes. And the count grows exponentially. And we answered this fourth question. That is, we determine the initial size of the bacteria, the doubling period, the population after 110 minutes, and the time it will take to reach the population 13,000. So let's see how to answer these questions. Since we know that the count grows exponentially, we are going to use the population exponential model, which is used for growth. That is, we represent the population as P of t, and this equals P naught e raised to the power of kt, where P of t represents the count of bacteria at time t, and P naught represents the initial size. This is population at time t, and k is the growth factor which we have to determine, and t is the time in minutes. So let's see how to determine the values like P naught, K, so that we can answer these questions. I'm going to use this information first to determine the growth factor K. So first I write P naught. I'm sorry, this is P of t, and this equals P naught e raised to the power of kt. And after 20 minutes, we know that the count of bacteria is 600, which means when t equals 20, that is P of t, which is P of 20, and this equals 600. So we plug in t equal to 20 into this equation, also P of 20 by 600. So therefore, this will become P of 20 equals P naught e raised to the power of k times of replace t by 20. Replace P of 20 now by 600. So we have 600 equals P naught e raised to the power of 20k. Let's say this is equation number 1. Now let's use the other information. That is, the count of bacteria is 1600 after 35 minutes, which means when t equals 35, this is in minutes, P of 35, this equals 1600. Once again, we plug in t equals 35 into this, and P of 35 as 1600. So when we do that, we get P of 35, and this equals P naught e raised to the power of k times of replace t by 35. So it is k times of 35. Now P of 35 is 1600. That is the bacteria count after 35 minutes, and this equals P naught e raised to the power of k times of 35k. K times of 35 equals 35k, and so we get another equation. Let's say this is equation number 2. Now we can divide equation 2 by 1 to solve for k. So I'm going to perform this operation, that is equation 2 divided by equation 1. And when we do that, we should divide the corresponding sides. That is left side of equation 2, which is 1600. This is divided by the left side of equation 1, which is 600. And this equals the right side also we should divide. That is P naught e raised to the power of 35k. This is the right side for equation 2. And the right side for equation 1 is P naught e power 20k. This one is P naught e raised to the power of 20k. Now we can cancel this P naught with this P naught, and this one can be simplified to, we can cancel the trailing zeros. So this one is reduced to 16 over 6, or in fact 16 over 6, and this equals 8 thirds. So let's put 8 third over here, and this equals here we get these two are like terms, that is e raised to the power of 35k divided by e raised to the power of 20k. So according to the exponent laws, we can simplify this by using the division property, that is e raised to the power of 35k minus the e raised to the power of 20k. So I subtract 35k with 20k, just means we get 35k minus 20k, which is 15k. So this one is e raised to the power of 15k. Now we apply natural logarithm to both sides so that we can solve for k. That means natural logarithm of 8 thirds. This equals natural logarithm of e raised to the power of 15k. Now using the power rule of a natural logarithm, we can bring this in front. That is, this will get this 15k gets multiplied with the natural logarithm of e. Remember that the natural logarithm of e, the value of this is equals 1, which means we replace this by 1. And so 15k times 1, we can just remove it because it's 15k. So on the right side, we have 15k, and on the left, we have natural logarithm of 8 thirds. Now divide both sides by 15 and solve for k. Let's rearrange for k, and this equals the natural logarithm of 8 thirds divided by 15. We can plug this expression on the right side into the calculator and approximate to 4 decimal places. So when we do that, we get 0.0654. This is approximated to 4 decimal places. So first we have determined the value of k, which helps us to determine the initial population size. Okay, now that we have determined the value of k, we can plug it into equation 1 or equation 2 to determine the value of p naught, which basically represents the initial size of the bacteria. So I'm going to plug it into equation 1. So therefore this becomes 600 equals p naught e raised to the power of replace k by 0.0654. This will become 20 times of 0.0654. And so we can solve for p naught from this equation. Therefore p naught equals 600 divided by this expression. So we write this as e raised to the power of 20 times of 0.0654. And we determine this numerical value by plugging into the calculator. And so when we do that, we get p naught equals 162.2, and this one is approximately 162. That is, p naught represents the initial size of the bacteria. So therefore, we see that initial size of the bacteria equals 162. And this answers the first question, that is initial size, which is 162. So I'm marking 162 over here. We now answered this question, that is we have to determine the doubling period. So for that we can utilize the formula, that is this t is equal to natural logarithm of 2 divided by the growth factor k. So let's substitute the value of k over here. So this becomes natural logarithm of 2 divided by k is 0.0654. And so when we plug this expression into the calculator, we get approximately, this one is 10.6, and this is in minutes. And so therefore the doubling period is 10.6 minutes. So I mark this one is 10.6 minutes. We now determine the population after 110 minutes. So for that, we first rewrite this population model using the values of P naught and the growth factor K, which we have already determined. So we write P of t. and this equals P naught is replaced as 162 e raised to the power of replace k by 0.0654 times t. Now we should find the population after 110 minutes, and this means we looking for p of t when t equals 110. So replace t by 110 into this equation. So we get p of 110, which represents the population after 110 minutes. And this equals 162 e raised to the power of 0.0654. Replace t by 110. So this becomes 110. Now we put this expression into the calculator. That is, first we multiply these two quantities and then raise this to the power of e, and finally multiply with the multiplier 162. And so when we do that, we approximately get 215,690. This is rounded to a whole number since this one represents the bacteria count. So therefore, the population after 110 minutes equals 215,690 bacteria. So here we can write 215,690. We now determine the time it takes for the population to reach 13,000. So here P of t is 13,000, and we should determine the corresponding time when the P of t, that is, the population is 13,000. So let's use this population model. Replace the P of t by 13,000. So this becomes 13,000, and this equals, on the right side, we have 162 times e raised to the power of 0.0654 t. First, we divide both sides by 162. So let's do that. And so here we get this one. Let's keep this as 13,000. This is divided by 162. And this equals, these two will become 1, cancel each other. And on the right side, we will have e raised to the power of 0.0654 t. Now to solve for t, we should apply natural logarithm on both sides. So we have natural logarithm of 13,000. This is over 162. And this equals natural logarithm of e raised to the power of 0.0654 t. So again, we use the power property of natural logarithm so that this could be put in front. And so this becomes 0.0654 t times natural logarithm of e. We know that natural logarithm of e equals 1. So when we multiply this with the natural logarithm of e, which is 1, and this means we should have the same number, that is 0.0654 times t. And so we can now solve for this t. Therefore, we write t. This equals, on the left side we have this expression, and this should be divided by this quantity. So this is natural logarithm of 13,000 over 162 divided by, this is divided by 0.0654. And so we plug this expression on the right side into the calculator to find the numerical value, and we approximate t. This one is approximately 67 minutes. And so therefore we see that it takes 67 minutes for the population to reach 13,000. So here we mark this one is 67 minutes. So thus we have answered all parts of this question.